We've learned how to identify chiral centers and to determine R and S configuration. Now we can apply these tools to determine the stereoisomeric relationships between two molecules. Let's start with these molecules. The first thing we want to do to confirm that these are stereoisomers is to ensure that all the atoms are connected in the same place. So we can look here and see that the chlorine is connected on this second atom, this ethyl group on this fourth atom, and this bromo group right here. Next, we'll want to identify the chiral centers in both of these molecules, or which carbon atoms are connected to four other groups. And those would be here, 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 and for this molecule, here, here, and here. Since these are stereoisomers, their relationship can fall into one of two categories. We've already discussed enantiomers, which would be non-superimposable mirror images. But if you've read through the book and or the online text, you've learned diastereomers, which means stereoisomers that aren't superimposable mirror images. An easy way to determine this relationship is to take, in this case, the molecule on the left, draw its enantiomer by switching all of the wedges and dashes, and see if it matches the molecule on the right. Now, pay attention to the fact that both of these molecules are in the same conformation. And by that, an easy way to tell is that all of the lines are drawn in the same orientation. As you can see here, we have the shape, same here, and etc. As long as those lines overlap, they're in the same conformation, and that's going to become important in our next example. Going on, let's go ahead and draw the mirror image, or the enantiomer of the molecule on the left. So I'll go ahead and draw this chain. Then we're going to have the bromine on a dash, this ethyl group on a wedge, and this chlorine on a dash. Now we want to see, does this match up with this? We have the chlorine on the dash, the ethyl group on a wedge, but these two bromines here don't match. One's on a wedge and one's on a dash. Because of that, these aren't enantiomers, they're diastereomers. This shows how you can easily draw out the enantiomer of one molecule and compare it to what you're given. But you have to be careful with this technique, as we'll see in the next example. Let's apply the process we applied in the previous example to this one here. Now, the first step we'll want to take, as we did before, is to confirm that the connectivity between these atoms is the same. On the left, we have a hexane parent chain, and we have the same on the right. On the left, we have a chlorine atom connected in the middle of the molecule, as well as the bromine here, and we see the same thing on this molecule. But you should notice a little bit of a difference between these molecules. And that difference is coming from the fact that they're in different conformations. There are two ways we can get around this. We can either take this part of the molecule and spin it around this single bond to achieve the same conformation we observe in this molecule. Or we can apply RS configuration to the chiral centers in these molecules and determine the relationship based on that. Since the first method I mentioned is very difficult if you haven't had a lot of practice thinking in 3D, we'll go ahead and do the second method. First things first, we'll want to identify our chiral centers. With the molecule on the left, we'd have that here, and with the molecule on the right, we have that here and here. Now keep in mind the thought process behind that is that these atoms, the chiral centers, are connected to four different groups. Now it's time to assign RS configuration, and we'll start with the carbon that's connected to the chlorine on the molecule on the left. So we'll want to assign the priorities to the respective positions. So I'll go ahead and redraw that part of the molecule right here. And you should realize that there's a hydrogen in the back that's on the dash with this chiral center. As you go through the prioritization, well, we know if the hydrogen's on the back, that's going to be a 4 in the back, which will make things easier for us. We know that the chlorine is going to be number 1 because the other two positions are both carbons. Now, since the other two are both carbons, we have to see what they're connected to and determine the prioritization based on that. The carbon on the left is connected to another carbon and two H's, while the carbon on the right is connected to a bromine, a carbon, and a hydrogen. And before, when I said two H's, I was referring to hydrogen atoms. Since bromine has a higher atomic number than carbon, the carbon atom on the right wins out in prioritization. So that'll be the 2, and the other carbon atom will be a 3. Following the Kahn-Ingold pre-log rules, we'll draw our circle following the 1, 2, 3, which, since we're going clockwise, that would be an R configuration. So I'll draw an R by that chiral center. So let's move on to the carbon on the right. And we're going to, it's going to be a little tight here, but I'll go back and erase what we've written here while keeping the other example up so you have a reference, so that we have room for determining the RS configuration of the other molecule. One thing you should notice here is that in this case, the hydrogen is on the wedge. So when we go and assign priority, the hydrogen is going to have the 4. The 1 is going to be assigned to the bromine atom, and once again we have these 2 carbon atoms. If we do the process, we know that the 1 on the left is attached to chlorine, carbon, and a hydrogen, while the 1 on the right, and by that I mean that atom, we are attached to a carbon, a hydrogen atom, and another hydrogen atom, which means that this atom wins in prioritization since chlorine beats out carbon, which would mean that this carbon right here gets the 2, and this one gets the 3. Before, in one of the previous videos, we actually switched these numbers around to put 4 in the back, but there's an easier way to do that. Let's go ahead and follow the 1, 2, 3 order, which would be a clockwise, and we'd expect this to be an R configuration if the 4 were in the back. Since the 4 is actually on a wedge going towards us in the front, instead of saying it's clockwise, we'll just reverse the direction, and that is actually an S configuration. And I'll put that by the atom right here. Now before we move on to the other molecule, I'll go ahead and erase, make some room for us. But what I just did there was another method you can use to avoid having to switch the positions of those numbers all the time. Now, one thing to notice with the molecule on the right is that there's something noticeably different about the configuration of this carbon atom and this carbon atom, and I could also say chiral centers, because everything, all the connectivity is the same, the orientation is the same with the hydrogen in the back, so we know that this is still going to be an R configuration on this atom, which saves us some time. But we will have to determine the configuration for the chiral center over here. So I will go ahead and draw that out. We have the dash and the wedge. Once again, the wedge is representing the hydrogen atom. As we go through and assign prioritization, we know that the 4 will therefore be on the wedge. The bromine will be the highest atomic number, so then 1 and the highest priority will go here. Now we have to decide between these 2 carbons, and we'll do the carbon on the left is attached to a chlorine, a carbon, and a hydrogen, while the chlorine here, down, is attached to a carbon, a hydrogen, and a hydrogen. And once again, the carbon that's connected to the chlorine wins out because chlorine has a higher atomic number than carbon, which would mean that this carbon here would be 2, and the 1 down here would be 3. Once again, the 4 is in front, so we can just flip things around once we know which direction the circle is going in. In this case, it's going counterclockwise, which should make it an S, but since it's 4 is in front, we'll go ahead and switch that to R. So that would mean that this chiral center over here is R. Here's where we determine the stereoisomeric relationship between these 2 molecules. If these 2 molecules were enantiomers, they would have the exact opposite configurations with R and S. While the chiral center that is attached to bromine changes configuration, the chiral center associated with the chlorine atoms, it doesn't change. And since these configurations aren't the exact opposite as we'd expect in enantiomers, these are therefore going to be diastereomers. So through this example, you can see a way to define the relationship between stereoisomers when the configuration is a little bit different. And that way you can confirm your answer instead of having to plow through all this thinking in 3D.